Hi everyone, welcome back. In this video, we are going to start Unit 2 Fundamentals of Machine Learning, which focuses on data handling and artificial neural networks. This unit forms the backbone of understanding how raw data is prepared and how neural networks can learn from it. As you can see in data handling and artificial neural network, before any machine learning model can work effectively, data must be properly handled, cleaned, and prepared. At the same time, we will also study artificial neural networks which are inspired by the human brain and form the foundations of deep learning. Let us look at the syllabus topics covered in this unit. This unit includes feature selection mechanism, imbalanced datasets, outlier detection, artificial neural networks including backpropagation, and finally applications of machine learning. Data handling. Data handling is the process of collecting, organizing, pre-processing, storing, and managing data so that it is accurate, consistent, and suitable for analysis or machine learning models. In machine learning and data science, data handling includes data collection, data cleaning, something like handling missing values, noise, and outliers, and a data transformation like normalization, scaling, and encoding, data integration and detection, and preparing data for effective model training and evaluation. Types of data. Data can be broadly classified into two main types, quantitative data and qualitative data. Quantitative data represents numerical values that can be measured and counted. Examples of quantitative data includes age, height, and income. These data types are typically analyzed using mathematical and statistical techniques. Qualitative data, which consists of non-numerical information often categorized into distinct groups or qualities. Examples of qualitative data includes colors, emotions, and customer satisfaction ratings. Qualitative data is often analyzed through categorization and thematic analysis. Types of data handling. Data handling techniques encompasses a wide range of methods to effectively process and present data. Here are some common types of data handling. Bar graph, which is used to display categorical data using rectangular bars. For instance, a bar graph can illustrate the sales figures of different products over a month. Pictograph, which uses symbols or pictures to represent data. For example, a pictograph can depict the number of books sold with book icons. Line graph. Line graph are ideal for showing trends and changes over time. They are often used in financial reports to visualize stock market fluctuations. Stem and leaf plots. Stem and leaf plots organize numerical data by separating the leading digits, stems, from the trailing digits, leaves. This helps in displaying the distribution of data points. Histogram, which provide a graphical representation of the frequency distribution of continuous data such as age groups in a population. Dot plots, which is used to represent data points. They are useful for visualizing individual data values and identifying patterns. Cumulative tables and graphs, which show the accumulation of data over time or categories. They are commonly used in finance to track cumulative earnings. Frequency distribution. Frequency distribution table summarizes data by displaying the number of occurrences of each value in a dataset. This is useful for understanding the distribution of data. What is data collection? Data collection is the systematic process of gathering raw information from various sources such as surveys, observations, or sensors. It is a fundamental step in data handling as the quality and accuracy of collected data greatly impact the subsequent analysis and decision making process. Feature selection techniques and machine learning. Feature selection is the process of choosing only the most useful input features for a machine learning model. It helps improve model performance, reduces noise, and makes results easier to understand. Helps in improve relevant and irrelevant and redundant features, improves accuracy and reduces overfitting, speeds up model training, and makes the model simpler and easier to interpret. Need for feature selection. Feature selection methods are essential in data science and machine learning for several key reasons. Improved accuracy, where model learn better when trained on only important features. Faster training, where fewer features reduce computation time. Greater interoperability, with fewer inputs, understanding model behavior becomes easy. Avoiding the cruise of dimensionality reduces complexity when working with high dimensional data. Types of feature selection methods. There are various algorithms used for feature selection and are grouped into three main categories, and each one has its own strength and trade off depending on use case. Filter methods, wrapper methods, and embedded methods. In filter method, which evaluates each feature independently with target variable, feature with high correlation with target variable are selected as it means this feature has come relation and can help us in making predictions. These methods are used in the pre-processing phase to remove irrelevant or redundant feature based on statistical test or correlation or other criteria. Some of the common filtering techniques includes information gain, which measures detection in entropy when a feature is used. Chi-square test, which checks the relationship between categorical features. Correlation analysis, which is a statistical method used to evaluate the strength and directions of a relationship between two or more variables. Wrapper methods, which is also referred as greedy algorithm, the train algorithm. They use different combinations of features and compute a relationship between these subset features and target variables, and based on the conclusion, addition and removal of the features are done. Stopping criteria for selecting the best subset are usually predefined by the person training the model, such as when the performance of the model decreases or a specific number of features are achieved. Some of the wrapper method techniques are forward selection, which starts with no features and add one at a time based on improvement. Backward elimination, start with all features and remove the least useful feature one. Recursive feature elimination removes the least important features step by step. Embedded method, which perform feature selection during the model training process. They combine the benefits of both filter and wrapper methods. Feature selection is integrated into the model training, allowing the model to select the most relevant features based on training process dynamically. Choosing the right feature selection method depends on the several features or factors. Dataset size, which filter methods are generally faster for larger datasets, while wrapper methods must be suitable for smaller datasets. Model type, some models, like tree based models, have built in feature selection capabilities. Interoperability. If understanding the rationale between feature selection is crucial, filter methods might be the better choice. Computational resource. Wrapper methods can be time consuming, so consider our available computation power. What is imbalanced dataset? In data science and machine learning, a common challenge that practitioners often encounter is dealing with the imbalanced dataset. An imbalanced dataset refers to a situation where the number of instances across different classes in classification problem is not evenly distributed. In simpler terms, one class has significantly more example than the others. This can lead to biased model that favor the majority class and struggle to probably learn the characteristic of minority class. Understanding the basics. The data set is typically considered imbalanced when one class significantly outnumbers the other. For example, in a binary classification problem, you might have only two classes, either it is 0 or 1. If 90% of the instances belong to the class 0, and only 10% to the class 1. The dataset is highly imbalanced. While this issue can arise in multi-class classification as well, the term is most often used in context of binary classification. And here are the some of the real world example includes fraud detection, where only a tiny percentage of transactions are fraudulent. Medical diagnosis, diseases like cancer or rare genetic condition affect a small percentage of the population. Spam detection, most emails are legitimate and only a small portion or spam. Why imbalanced dataset are a problem? Imbalanced dataset can cause issues because most machine learning algorithms assumes that data is evenly distributed across classes. When the assumption is not met, the model tends to become biased towards the majority classes. This can result in the model performing well on majority class but poorly on the minority class, which may be the more important class in some contexts, example fraud detection or disease diagnosis. Biased application. The model may predict the majority class more frequently, leading to highly accuracy but poor performance on minority class prediction. Low sensitivity. Sensitivity, also known as recall, for the minority class may be low, meaning the model failed to identify many true instances of that class. Poor generalization. A model trained on an imbalanced dataset may not generalize well to new, unseen data, especially for minority class prediction. Techniques for handling imbalanced datasets. There are several techniques which can help address the issues associated with imbalanced dataset. Some of the most common methods include resampling techniques, use appropriate evaluation metrics, and algorithm level solution. In resampling techniques, there are two: oversampling the minority classes and undersampling the minority classes. Oversampling the minority classes, which involves increasing the number of samples in the minority class by duplicating them or creating synthetic samples using techniques like SMART. Nothing but synthetic minority oversampling technique. In undersampling the majority class, this technique reduces the number of samples in the majority class, helping balance the datasets. However, it may lead to information loss if too many samples are removed. Next, use appropriate evaluation metrics. Precision, recall, and F1 score. These metrics provide a clearer picture of model performance, especially for the minority class. Receiver operating characteristic area under curve. A useful metrics that evaluates how well a model distinguishes between the classes. Confusion matrix. This matrix helps visualize the number of true positives, true negatives, false positives, and false negatives, often offering deeper insights into model performance. Next, algorithm level solutions. Cost sensitive learning. Modify the algorithm to give higher importance or cost to the minority class, thereby forcing the model to focus more on correctly classifying the minority samples. Ensemble methods. Algorithm like random forest, gradient boosting, and XGBoost can be effective for handling imbalanced datasets, especially when combined with resampling techniques. Data augmentation. For complex tasks like images, classification, generating new data for the minority class through augmentation, example, rotating, flipping images, can help balance the dataset without affecting the model performance. Next, anomaly detection. In some cases, instead of trying to balance the dataset, you can approach the problem as an anomaly detection task where the minority class is treated as an anomaly or outlier. Thank you. In the next video, part 2, we will see the remaining topics. Thank you.